And so what I've been working on for a while now has been creating a low-cost, non-invasive, brain-controlled robotic arm controlled by a combination of brain waves picked up by non-invasive these neural electrodes placed in the scalp, as well as some head gestures.
Welcome everybody to a very special episode of Invent-A-Phone. We have Ben Choi, who is one of the finalists in our Wevolver Make It Real 3D printing challenge, and we're going to help him today add some special finishing touches to the design of his robotic arm. So welcome to the show, Ben.
Yeah, thanks. I'm really excited to be here.
Awesome. Cool. So do you want to tell us a little bit about your invention here before we dig in?
Sure. Yeah. So I guess the initial idea for my project came when I watched this documentary about neural interfaces being used to control prosthetic limbs. I was really impressed by the applications of the technology, but also I was alarmed that, these forms of brain control require hundreds of thousands of dollars in a really risky open brain surgery. And so what I've been working on for a while now has been creating a low-cost, non-invasive brain-controlled robotic arm controlled by a combination of brain waves picked up by non-invasive these neural electrodes placed in the scalp, as well as some head gestures. And so the arm is entirely 3D printed so far, and where polySpectra comes into play is that the current 3D printed model still has some durability concerns that really prevent it from moving out of the prototype phase. And so my hope is that with the help of Core Alpha, I can really turn my robotic arm to something that is viable for daily use. So
Awesome. That's amazing. Just out of curiosity, what did you design this in?
I used a combination of various just free online softwares. I used Blender as well as Tinkercad and Onshape. So
Wow, awesome. That's really cool. So we're not sort of showing it fully in order here, and some of them are rearranged, but we obviously got so maybe from the fingers all the way to the arms, we got the finger pieces here, and these have these through holes. So what goes through these?
yeah, so right now I have like this plastic wire, and
Okay.
when tension is applied to that wire, the fingers can curl inward, so that kind of provides the mechanism for the flexion and extension.
Okay, awesome. And so there's sort of tension in this wire through that's kind of how it's gripping. And then it's got to go through the hand, and we're going to spend a good amount of time working on this hand piece here. So you can see all the through holes of the hand here. And then just so people understand a little bit about the fold, so then this is kind of, what are you calling this? Kind of the wrist, I
Kind of
guess?
like a wrist piece. Yeah,
Okay, a
there's a
wrist piece.
motor located in the hollow chamber that
Okay.
which the wires connect to.
So this motor runs the fingers?
Yes.
Okay, awesome. And then finally, we've got the forearm enclosure here. And then is there another motor in here, or what's in
Yes,
here?
so there's a motor inside that chamber as well as the CPUs. That motor provides wrist rotation, and then connecting to the back of that, there's also another motor setup that's like this dual axis elbow.
Awesome. All right. So that I feel like we're pretty oriented here. So what we've done, I've loaded all of Ben's parts in here. We've done a little bit of housekeeping in terms of making sure that all of our meshes are manifold and things of that nature. So the very first thing that Ben had asked us to do here was to really focus on the hand. Ben, can you explain just a little bit of what your goals are?
Since the hand is located the furthest from that elbow motor, which it really applies, especially when it's heavy, it applies a lot of torque to that motor. And so I'm really hoping to use lattices to lightweight out the hand.
Okay, awesome. So we can see here in the cutaway that the current design of the hand is pretty solid. So he's got these through channels to connect those wires that are the mechanism for pulling the fingers down. But the rest of the hand body is a solid block. And so what we're going to do is we're going to use the latticing in feature in topology here to kind of lightweight that for him. Just to quickly walk through what we did here for Ben. So one of the tricky things sometimes with bouncing STLs is making sure that the mesh that we're exporting is sort of what people call it like a clean mesh. And so we can actually see in the original mesh that we don't have a manifold mesh, and there's some self-intersecting points. So I'll just show people really quickly that are interested in NTOP a quick way of cleaning things up. So what I've done is I basically split the mesh, Ben's original mesh, into two, and I don't even know where the second one is going to be. And then I basically filter away. So there's some kind of like erroneous, really tiny mesh, and I basically am filtering away anything that's smaller than a millimeter cubed, which is pretty tiny, so 1 by 1 by 1 millimeter. So there's obviously like some little dangling triangle somewhere that we're deleting, and we're cleaning that up, and that's going to help us just move quicker through NTOP without any errors. So we've fixed the hand model here, and then we're going to turn it into an implicit body through a voxel grid. And this is very important for just capturing curved surfaces in a computationally efficient way. So maybe just a quick reminder for folks is, so in NTOP, what does the implicit body mean? It basically means we've got a field, and we can manipulate the part and treat it as a field. And so that's a really fast way of doing quite complex calculations. So the first thing that I tried when Ben first wanted to kind of lightweight this was a very simple block that is called the shell and volume lattice. So what we did was, so we're creating a shell that is 1.5 millimeters thick, and then we're creating a lattice inside it with a 7 millimeter period. It's a body-centered cubic BCC lattice, which is very strong and self-supporting. And then we made the struts of that lattice 2 millimeters thick. So Ben, what do you think about this one?
Yeah, I really like it. I think it definitely does a lot of good work in lightweighting out the part. I'd be interested in seeing other lattice designs as well.
Okay. Ben thought, all right, it's okay. Pretty cool, but we could do better. So basically, one of the other thoughts that we had was playing around with things like creating like Voronoi lattices, which I think are a little bit too open of a structure for Ben's taste. Am I correct?
Yeah, yeah.
So we wanted to stick back to things that are let's say have solid faces. So this idea of like a shell and a lattice. So then one of the other fun light-weighted structures that is possible is a gyroid. And again, this would be an example of if we created a gyroid through the entire thing, but then you can see that would include the surface. And so the final one that we landed on together that seems pretty cool, and Ben, you can still change your mind, is this shell and gyroid. So basically here, similarly to the one above, we've got a shell, so this outer perimeter of 1.5 millimeters in, so we're preserving all of those little channels, we're preserving the envelope of the shape, and then inside we've got this really fun gyroid looking structure, and we're using this at about a 2 millimeter approximate thickness, so make sure we have really strong uncrushable hand. So Ben, any comments on this one?
Well, I guess it's really the best of both worlds. I'd like the kind of enclosed structure as you mentioned with the shell, but at the same time, I really like that gyroid pattern. So yeah.
Okay, so it's functional and aesthetically pleasing. So we're going to try to build this for Ben. And I think one of the things that can be challenging for a shape like this is with any kind of shelling structure, right, is the shell creates this internal volume, and we're doing, vat photopolymerization style printing. So there's a liquid resin that we're solidifying, and you could actually tell that as complex as this is, and even though it kind of seems like there's all these open channels, there's actually no way out of that shell. And so even though the gyroid is co-continuous through that volume, the resin that would be left behind would be stuck in the hand. So we're going to need to create a way out. And so let's see if in just a minute or two we can kind of create a drain hole. So Ben, what's your ideal place to have a sneaky little drain hole that we can pour the resin out of after
Yeah,
it's
well, I guess
printed?
I'd like to preserve the integrity of the channels where the wires go through, but maybe,
Okay,
in
yeah,
the
we gotta leave
bottom,
those. Okay.
yeah, but I guess in the bottom, it is of the hand, there is kind of this wider slot, so maybe that could be a good place to drain out.
Okay. So this slot that's coming through there. Okay. So here's what we're gonna do. We're going to try something very simple. So first I'm going to find the middle of this structure here. Let me get the cutaway. So see that blue dot? That is the centroid of the bounding box of this hand. And then so that's just kind of going to orient me. So so we're going to take a sphere, and we're going to maybe actually we want to find the well, there's a few ways that we could do this. We've got a sphere here, and so maybe I'll just show a couple ways. We could literally drag. This is sort of the manual way. I can drag this sphere around to where his slot is here, and we can line it up. So that's a little bit. So this is, I don't know, maybe bigger than a radius of 5. That's pretty big. So I think we probably need, I don't know, a couple millimeters to be able to, well, let's just make it big enough so it can drain out of both sides. How about that? So basically we got this. So this is going to be our subtraction body to create a drain hole, right? And then what we're going to do is we're going to say, okay, so this is called Ben's favorite. And then we're going to subtract from Ben's favorite the sphere here. So you can, well, let's get a better kind of cutaway view again. So in that channel, we've now got two different, oh, that one didn't quite make it all the way through. So on this side, we didn't actually make it all the way through. And so there's two ways that we could solve for that. We could make his, the sphere a little bit larger. And there you see, we're just barely starting to punch through. On this side, we made it through because you can see it kind of disappear. But then we can also, so we can make it just a little bit bigger until we punch through, or we can also play around with having a slightly bigger blend radius. So that would be another way to make more room for this hand. Let's see. So what do you think about that? We're sort of like hiding
Yeah, that's
Here,
great.
actually, let's look at it from the other side too. Oops. All right. So let's look. So there we go. So in that slot in the hand, right around the middle, we've got a sneaky way to get our resin out. And one of the interesting things about, we'll have to see if this ends up being true in practice, but in theory, so one of the interesting things about a gyroid, I want to make it just a little bit bigger so that we're really sure that we can clear that. Maybe 5 millimeters was the best way to go. But one of the fun facts about a gyroid is that it's co-continuous, right? So every part of the solid part of this gyroid is connected to every other part, and also vice versa. The empty space is also co-continuous. So in theory, as long as we've got some path into the inside of this gyroid, we could pour out any remaining resin that's trapped in there. Now, in practice, it may not be quite that easy, so we'll have an update when we see if this actually works. But so you can see we've got this kind of sneaky way where I think nobody other than Ben will notice. No one from the outside of the robot arm will notice that we kind of created this sneaky drain hole to be able to pour out any of the resin that got trapped inside this body. So Ben, are you okay with that?
Yeah, it's awesome.
This is manufacturing limitations that most people don't necessarily think about, but I think we solved for it in a pretty cool way. And the other important thing is that because the gyroid is like kind of self-supporting by nature and continuous, is that even though we subtracted that away, we're not worried at all about it printing, right? Because you know, it's, you know, we're not worried about its structural integrity because of that structure. So that's another really nice aspect of this sort of shell and gyroid strategy. Okay, so that is awesome. So this is going to be with drain hole. We're going to save that one as a variable to use later. So Ben, are we okay with the hand?
Yeah, it's great. It's great.
All right, awesome. So let's so with the hand, you know, we've got our shell and gyroid, we've got our drain hole. So then there was one other thing that we were working on for Ben, which was we were kind of looking at some of these. Let's see, let's just look at all of them at once here. Where are they? There we go. We were kind of looking at some of these and saying, you know, these are awesome. And, you know, Ben has designed these different faces to kind of snap, well, not necessarily like lock snap, but like to fit together with no seams, right? But there's a decent amount of room to play in terms of, you know, kind of big straight faces that we could play with and maybe do something fun and creative. And so let's now take a look at what we're thinking about with, so I think well, first, actually, here, let's look at this one. So one of the original ideas I have was playing around with this idea of taking a gyroid field, right? And then, and then offsetting the bodies by that. And so I thought this looked kind of cool. Ben, what are the problems with this one?
Yeah, I guess the main concern is maybe the uneven texture of the face. It just might interfere with the way the parts fit together, or like
Right.
how you can attach various motors. So
Right. So this on this edge where it's got to connect to the other one, we'd have to do some, it's not that we couldn't address it, but it would be kind of decent amount of work. So anyways, that was kind of one of the field-driven texture ideas that we had. But then I think where we ended up wanting to go with this was thinking more, so we didn't like the idea of doing a Voronoi for the, oops, let me turn off the field viewer. We didn't like the idea of doing a Voronoi as the structural component itself. But where we ended up playing around with was taking this idea of a Voronoi lattice and using the Voronoi deboss, which you can find here in the architected materials. Where is it? Right here, Voronoi deboss section, to play around with subtracting kind of a Voronoi texture from the parts. And so maybe Ben, let's just show them like a few different iterations here. So we were kind of playing around with different densities. So I guess I don't know, what's interesting to you or exciting to you about these textures, and what do you think we should be optimizing for?
Yeah, I guess, I just really like the way it looks. It's not as obtrusive, I guess, as the gyroid field. It's the design sort of reminds me of, like, I don't know, the superhero, The Thing or something. I think it just
Okay,
looks cool. Yeah, yeah.
that's cool. I like the Thing example. I guess another thing I'll highlight is that, let's say that we had picked emboss. This would actually be, I'll let this run. So we picked deboss for a reason, because so he's got to have these mating faces, right? If we had picked emboss, right, then now, hold on, let me make it more obvious. I'll make it kind of extra thick just so that it's obvious what's happening. It would actually get in the way of those matching faces. So we're going in from the surface a little bit, just to kind of texture it for him. And then we were playing around with, okay, what's the right size? And, that one, I don't know, is kind of like, do you know the Ninja Turtles? Is that a thing still? This was a
A
thing when
little
I was
bit,
a kid,
yeah.
Teenage Mutant Ninja Turtles. So
Mhm.
anyways, that was kind of like a turtle shell. We can bring up the counts here on it to get it more refined. And I think we decided to end up somewhere around, what did we say, Ben? 500
Sure, yeah.
was kind of a good number. So again, actually, this is something that we could play with, which is one of the fun things about things being sort of more functional in NTOP is, one of the things that I played around with in the past is, instead of explicitly calling on the number of cells, you could actually think about a density, and you could, for example, check the surface area of the part and then adjust the number of cells to be for the density. So anyways, let's show them what happened when, so basically, so Ben, I guess, Ben, you liked this one, and then the next request was, well, they got to all look the same, right?
Hmm.
So what we did for Ben was, I'll just walk people through really quickly how we did that in 1 second, which is took all of his STL meshes into a list. We merged those meshes, and then we treated them just like we did before. We went through a voxel grid, got them all as implicits. So now we have all of his parts as implicits. And again, they're not sort of particularly oriented in any specific way. We didn't kind of clean that up, but it doesn't matter, because now, instead of running deboss just on the arm, I can run deboss on the all, and here we go. So hold on, let me crank up the resolution on this so we can really see what this is going to look like. Here we go. Now that's looking good. So what do you think about this, Ben? We got,
I like it. Yeah.
you like it? All right. So we've got this sort of matching texture across all of the parts. And I think this is really one of the powerful aspects of NTOP is that we built it out with one part first, and then we were able to just combine everything together. Maybe I went a little bit too thick on the grooves for your fingers, so I'll dial that back a little bit. I didn't realize I punched some holes in the walls of your fingers. Sorry about that, Ben.
No worries.
But the yeah, I think we're liking how this is looking. I'm pretty excited to print this. So yeah, Ben, thanks for letting us, get creative with your awesome robot arm here.
Yeah, no problem. Thanks so much for having me.
Yeah. Anything else that you want to discuss in terms of the designs here, or before we go to printing the full thing, anything else you want us to work on for you on the digital side?
No, I think it looks pretty good. Yeah. I'm really satisfied with how it's shaping up. So.
Okay, awesome. Well, we are super excited to print this for you, and yeah, I hopefully this was a educational kind of walkthrough to be able to record and show that to other people. And so we will yeah, thank everybody for their time, and would love to hear from any of the folks viewing this in the comments below. What do you think? What should we have done with Ben's arm that we didn't consider? What would be even cooler? Or how might you apply this to your invention? So let us know in the comments below. And thanks again, Ben.
Yeah, thanks so much.